Hello everyone, my name is Leonardo and I'm going to present this colloquium for the Computer Networks course, and I will show you the paper entitled Revisiting Congestion Control for Multipath TCP with Shared Bottleneck Detection. So this is the content of the paper. I will walk you through all those sections. So let's begin with the introduction. And the authors start talking about the IP and TCP protocols, which are layer 2 and layer 3 from the Aussie model, respectively. And there is a contrast between the present and the past. So in the past, we had a host with only one network interface and one connection between two different hosts. Now in the present, we have hosts with more than one network interface and more than one connection between two different hosts can happen. So this is how multipath can be used with cell phones. A smartphone can have more than one interface and use it at the same time. So one possible approach to that scenarios is the multipath TCP, MPTCP. It allows multiple network paths for a single data stream. It has the potential of a higher overall throughput in the connection, and there is application resilience in case of degradation or failure of links, and it's compatible with the current TCP protocol standards that we use nowadays in the internet. So we have the IETF working group. They are the people responsible for the development and the standardization of the pattern of the MPTCP. And there are available implementations on Linux and BSD based systems. And commercially available developments are not using MPTCP's full potential because they usually focus only on the resilience characteristics according to the authors. And there are the three main goals of the MPTCP. The first one is the improved throughput. So the performance of the throughput should be equal or greater than the throughput from a single path flow. This is the main reason behind the design of the MPTCP. And then we have the do not harm principle, which states that the resource consumption should be less than the if the consumption was by a single path flow. It guarantees fairness at the bottleneck link. The third one is the balance congestion. So if a path is congested, then we need to move as much as traffic as possible off it. So this addresses the MPTCP resource pooling principle, and this goal is subject to not offend any of the above, as the authors note. So what is a bottleneck? It's usually the lowest link of a circuit or path, or a link with the lowest throughput available or speed. So we have the shared bottleneck detection mechanisms. We lack practical SBD mechanisms available today, and many of them make the assumption of shared bottlenecks all the time. We will see the implications later. And this is an example of a shared and a non-shared bottleneck. For example, here we have the non-shared bottleneck, here the shared bottleneck between the client and server of MPTCP. A little bit of the motivation from the authors. They use the Linux implementation of MPTCP and use some algorithms for congestion control sitting here. Reno, for example, where each link applies a standard TCP congestion control and is uncoupled. And the other three are the linked increase adaptation, the optimized linked increase adaptation, and the balanced linked adaptation. They all three are coupled, and I will refer to them as Laia, Olaia, and Balaya. So a note on they use the versions for the tests. They use the version 3.14.33 to the Linux kernel, and for the MPTCP, they use the version 0.89.5. So they run some initial tests. They run two runs of TCP, TCP1 and TCP2, they called it. And there are two main flows, the subflow 1 and subflow 2. And they use ratio as a measurement as because it is the relative performance between the standard TCP and the MPTCP performances. So these are the initial results. So this one is for the non-shared bottleneck, and this one for shared bottleneck. Some notes on the results. So Lyle and Bolayer had consistent results, as you can see through the image. In the shared bottleneck scenario, the three algorithms perform around the 1.0 ratio, which is the expected optimal. Then we have the non-shared bottleneck scenario, where we had four algorithms test, however, pretty different ratios for three of them. So you can see a group here, and for Reno, there is a quite significant difference. Then we have the methodology of the authors. Uh, they follow the congestion control design goal 2, which stands that there should be fairness to the TCP if flows share a bottleneck with it, and fairness such that resource is limited to the amount of resources that would be used by a single flow on one of the paths, as I stated earlier. And the main objective is decouple subflows if they do not traverse a shared bottleneck. So Internet protocols lack ways of informing hosts regarding the shared bottlenecks. So usually the hosts infer these from packet loss and delay, and the MPTCP uses packet loss to indicate congestion. But the authors discarded some parameters to detect the bottlenecks and congestion. They discarded the packet loss because of a well operating network, for example, with less than 3% of um, packet loss, it would not signal frequently, so they can't calculate the where is the shared bottleneck, and loss is often not correlated across different flows, so it was discarded. And delays are frequent but noisy because we have delays can be calculated, but the problem is the induced delay between each node and each hop of the network. And RTT, round trip time, is easy to measure, but there is the problem of induced node of the return path. So what they used to detect bottlenecks and congestion was a mix of distribution of packet delay measurements and the grouping flows that have similar statistical characteristics. Uh, One-way delay potentially removes up to the half of the path noise because it's one way, as the name says, and it uses the mean on-way delay that is calculated through the relative on-way delay. The main advantage of it is that the sender and receiver clocks don't need to be synced to use this. So there is three main key statistics used to the algorithm SBD. The first one is skewness, which is estimated by counting the number of one-way delay measurements above and below the previous mean. The variability, that is the mean absolute deviation, and key frequency, which is quantified by counting and normalizing the number of times of a short-term mean one-way delay significantly crosses a longer-term mean one-way delay. And then we have the implementation that the authors did. As we can see here, in the first part, the sender transmits the local timestamps with great precision because they put 31 bits precision to the multipath TCP timestamps. So they calculate this timestamp and record it here, so it's sent to the receiver. Then in the step 2, the receiver extract the timestamp after the stack's basic reader checksum and calculates the relative on-way delay. And then the receiver inputs this to the shared bottleneck detection. And note that part of the shared bottleneck is in the user space. This is why the SBDU. And then the receiver feeds back the shared bottleneck detection information in step 4 to the sender here. Then in step number 5, the sender uses this information to couple flows in the same group and decouple those in different groups. So this is how the implementation of MPTCP SBD works. Then we have the emulation experiments. So they use the core network emulator. They revalidated some tests performed by other authors, and they use the same values for the shared bottleneck and non-shared bottleneck scenarios for comparing both scenarios. And they added the presence of a mix of synthetic background TCP and UDP traffic to make the simulation more realistic. Then there is the decision threshold, one observation every 350 milliseconds. The decision is taken based on a window of at least 10 observations. They use 10 because a larger window will increase the delay in reaching a decision, and a shortened window will not be able to effectively eliminate the transients. So some initial test comments. The shadow bottleneck, if the links in shadow bottleneck subflows are grouped in same group, then it counted as correct. And for the non-shared bottleneck, the distinct groups are counted as correct. So these are the results of the tests. And some notes. The authors note that the around 90% of the SBD decisions correctly group the subflows, and for the non-shared bottleneck, around 45% of the shared bottleneck detection decisions correct the subflows. Just for clarification, the shared bottleneck is on the left and the non-shared bottleneck is on the right side. So you can see the results here. And there is this line here, which is a gray line that represents the decision threshold, which is 5 out of 10. And they did that because they said they needed or aimed for 50% of observations consistency. So the same observation was made at least 5 times in this window. And they note that ties were resolved as grouping decision because they wanted to group more than ungroup to try to fix the behavior of the shared bottleneck scenario. So a note on shifting bottlenecks. A shifting bottleneck is just represented here. So we have, for example, a non-shared bottleneck, then a shared bottleneck. This is an example of shifting bottleneck. And the authors tested this shifting bottleneck experiment, and they showed that they said that the algorithm can make the correct observation, the correct estimation in 90% of the time above 75% of accuracy. So there is the results. And this is the results for the shared bottleneck and no shared bottleneck accuracy in the decision making. So here they highlight the results above 70% for each one of the tests, and here almost 100% certain. So they show here the throughput ratio during the tests. So as we can see, the shared bottleneck detection help increasing the ratio in almost every scenario in the non-shared bottleneck, which are those two, And for this one, which is the shared bottleneck scenario, it's not a problem because it keeps in around 1.0 ratio. The shared bottleneck versus the without shadow bottleneck detection algorithms. Here we have the red algorithm because they changed the discard policy of the routers in the network. So they changed the drop tail to the red random early detection. And these are the results, the new results. So the results were a bit affected, as you can see. And then they tried some different values of RTT for each link. For example, here we have 20 and 40 for the group 1 and 2, and so on for each one. And these are the scenarios for the non-shared and shared bottlenecks. And then we have the real network experiments. This is the architecture of the real environment. So the two main important things here are that the server is here and the Raspberry Pi is here, and it is connected to a DSL ROM router. And this environment is virtual, so they have virtual machines here. These are the main results of the experiment in the real network. So as we can see, we confirm that the shared bottleneck detection algorithm helps with the ratio, and for the non-shared bottleneck and for the shared bottleneck, it maintains the ratio, so that's fine, and it was expected by as we had these results in the simulations. And when we had shifting bottleneck experiments, this was the result. So again, above 75% almost all the time in the accuracy. Then we have the related work. In the related work, it's possible to note a evolution from algorithms behaving like TCP to coupled congestion control. Then coupled MPTCP applies resource pooling to shift away traffic to less congested paths. And here we have a summary of the related work, and this algorithm DWC is the closest one to the one that the authors of this paper propose, but it does not have the implementation. So the authors only show some of the details, and the the one made by them was actually implemented in the network stack. Then we have the conclusions and future work. So the main conclusions, we saw benefits of the shared bottleneck detection. The MPTCP coupled congestion control is overly conservative for multiple paths in the non-shared bottleneck scenario, as we saw the results in the beginning. The shared bottleneck algorithms, the shared bottleneck detection algorithm enables the decoupling and an increase of subflows congestion window. And the MPTCP SBD is a dynamic coupled congestion control mechanism for the MPTCP that is aware of the shadow bottlenecks, which was proposed. So they proposed, implemented, and tested the efficiency of the MPTCP SBD, as we saw. And after the testing a wide range of settings through emulations and even the real network, we conclude that the three main design goals were achieved. There is significant throughput gain in the non-shared bottleneck scenarios and no harm in the shared bottleneck scenarios. So for the future work, the robustness of the SBD algorithm against attacks should be investigated, as we can, as a receiver, could manipulate the feedback to gain unfair advantage. The performance relative to noisy statistics should be investigated too, because the lowest RTT of the MPTCP schedule can cause subflows such as sharing a common bottleneck to oscillate in their relative share of the available bandwidth. and possible advantages in turning SBD specifically to MPTCP congestion control, and there should be investigated more complex grouping algorithms that is improving SBD's robustness against oscillations from the link, and we should investigate the performance of MPTCP SBD for different use cases. For example, in single RAM devices to take advantage of multipath protocols, and hosts with dual stack MPV4 and MPV6 used for disjoint paths and presence of the bottleneck in the network. This is my reference to this presentation. Thank you for watching. See you around.